Okay guys, per request, a walkthrough on the calculations for the neutralization lab. Strangely, you also requested more pep and singing. Those are right out. Instead, if you need songs about thermodynamics, I would refer you to Flanders and Swann, the first and second law of thermodynamics. I will post a link to it down in the description. I hope that tickles your nerd funny bone. And for the rest of us, we're going to go dive straight into our calculations for the lab. Now we begin with determining the heat capacity of our calorimeter, because we're not going to assume that the calorimeter is ideal and doesn't interchange heat with our reactions. So instead, what we have to do is we have to do kind of a controlled setup involving melting ice in water and measuring the final temperature. That way we can calculate how much heat is exchanged between the calorimeter and whatever's inside of it. So for my made up data, I have 6 grams of ice at -1 degrees Celsius. I have 40 grams of water at 22 degrees Celsius, and I'm going to use 22 Celsius for the room temperature and the starting temperature of all the liquids for the rest of the lab. Final temperature after the ice is melted, 10 degrees Celsius. Here's the relevant thermodynamic data. Specific heat of ice and the specific heat of water and heat of fusion. I want to begin with the ice because its heat term is more complicated because it undergoes a phase change. So the first thing that we need to do is take our ice and warm it up from its initial temperature to the melting point, which is 0. So final temperature in the solid state is 0 minus the initial temperature plus. Now we need to melt it, so mass times heat of fusion plus. Now it's going to be liquid state, and we need to heat it up the rest of the way to the final temperature in the liquid state. So I'm going to switch gears and use the specific heat for water times final temperature minus 0, because the initial temperature in the liquid state is the melting point, 0 degrees. Just plug in numbers for that. I'm going to be using correct sig figs for all of these calculations, so if you kind of look askance at the answer that I get because it's different than your calculator, I've just rounded it to correct sig figs. So my Q of ice equals mass times specific heat times 0 minus a -1 plus mass times heat of fusion plus mass times specific heat of water, 4.184 times final temperature was 10 minus 0. Oh, and for my correct sig figs, it was -1.0. And that gives me Q for the ice, 2,270 joules. Now let's do water. Water is going to be a lot simpler because there was no phase change for the warm water that we put in. Just mass of warm water times the specific heat of water times final temperature minus initial temperature. So let's plug numbers in for that. 40.00 times 4.184 times 10.0 minus 22.0. And so that gives me -210 joules. And it is negative because this is heat that was lost by the water. The water was warm and it gave its heat to the ice. So you notice that we have a difference between these two numbers. In a perfect world where the calorimeter had 0 effect, these two numbers would be equal. The difference between the heat gained by the ice and the heat lost by the water is the amount of energy that went to our calorimeter. So now we can calculate the heat capacity of our calorimeter. and that is Q for the ice plus Q for water divided by the temperature change. And this is the temperature change for the calorimeter, which in this case is the same as the temperature change for the water, because it started at room temperature and ended at the final temperature. So if we plug numbers in here, switch to the pen, 2270 minus 2010 divided by a negative 12, but it's an absolute term, and so I get 21.7 joules per degree Celsius. So this means that for every degree that our calorimeter changes its temperature, it absorbs or releases 21.7 joules. And so we can use this in the calculation that we're interested in, which is the heat of neutralization, to figure out how much heat was produced that we didn't get to measure because it went into the calorimeter. So let's look at the heat of neutralization. Okay. My made-up data for this is I have 25 grams of 1 molar NaOH and 20 grams of 1 molar HCl. Now, if you remember the lab, it didn't produce that stark of a temperature change, but I'm kind of limited to that because the standard state delta H is defined at 25 degrees room temperature. We're close enough to not quibble over that. 1 atmosphere pressure and 1 molar concentration of all solutions. So kind of limited to that, even though in this case it doesn't produce a very dramatic temperature change. It is what it is for standard state. So one other thing to take note of here, we use masses to weigh these out in the lab because I don't have a large stock of volumetric flasks to do this properly and measure everything by volume. But we're going to assume, and it's a pretty legit assumption because these are fairly dilute solutions, that the density of these solutions is the same as that of water. So that means you can think of this 25 grams as 25 milliliters, because for water, 1 gram equals 1 milliliter. Also, we're going to assume that the specific heat of the solution is the same as that of water. So I can use the specific heat of H2O that we used on the previous slide. And that's also a fairly legit assumption because the reaction is producing water, so we're actually making water, so we can use its specific heat. And again, these are fairly dilute, so their specific heats wouldn't be far off. All right, and initial temperature of everything, 22 degrees again, and final temperature after the reaction is over, 27. Now before we get into it, I want to go back over the actual reaction that we did. We had aqueous HCl plus aqueous NaOH, and that made aqueous sodium chloride plus water, liquid state. And all of these three completely ionize in solution. They completely dissolve. So if I write this out as the ions, some H plus aqueous plus chlorine minus aqueous plus Na plus aqueous hydroxide aqueous sodium aqueous chlorine, I think you're getting the point, plus water liquid state. And our spectator ions were sodium, it appears on both sides, and chlorine, it appears on both sides. And that leaves us, our net ionic is hydrogen ion plus hydroxide ion makes water. And this is defined as the enthalpy of neutralization. So the heat produced by the reaction that we did is known as this enthalpy of neutralization. And this is the net ionic, and we got that from this reaction that we did. Any other acid-base neutralization could produce this, but what I want to point you guys out about this one in particular is that it's 1 HCl to 1 NaOH to 1 water. So if the enthalpy of neutralization is the heat released when we make 1 mole of water by reacting hydrogen and hydroxide, we've got that because 1 of this plus 1 of this makes 1 of this. So we're good to go. We don't have to do any real stoichiometric conversions here because everything is a 1-to-1 ratio. So sort of file this away when we get into the math a little bit later near the end of the problem, that 1 mole of hydrogen chloride equals 1 mole of sodium hydroxide equals 1 mole of water, which equals the enthalpy of neutralization. Okay, let me get a clean sheet and we will do the actual math. Okay, so the Q, the amount of heat released by the reaction, equals the heat that we measured in the solution plus the heat that was lost to the calorimeter. Okay. Our reaction was an exothermic one. The solution was heating up. So all of this is going to be a negative value because the heat lost by the reaction is the heat gained by these two. So we've got to keep our head screwed on kind of about sign conventions. You know, that's an exothermic reaction. My answer better be negative in the end. So that's why I've dropped that in there. So let's go ahead and work these out. The heat of solution is just the mass of the solution times the specific heat of solution times the delta T plus the heat for the calorimeter is just the heat capacity of the calorimeter times delta T. Okay. So let's plug in numbers. We had 45 grams total solution. You have to remember that I had 25 grams of NaOH and 20 grams of HCl. So my total solution's mass was 45. We were assuming that it essentially was the same as water, so I'm using water's heat capacity. And my temperature data was 27 minus 22 plus specific heat for the calorimeter, or the heat capacity rather, of the calorimeter, 21.7 times that same delta T, so 27.0 minus 22.0. This component is 940. This component is 110. So that equals a negative 1050 joules, which is a negative 1.05 kilojoules. And remember to express it in kilojoules because our accepted values for the delta H of neutralization, which is what we're trying to find here, is negative 55.8 kilojoules per mole. Now bring the accepted value up because one, we want to compare ourselves to that, but also to take note, this is kilojoules per mole. This is the just absolute amount of heat that we released. We need to divide that out by the number of moles of water we produced so that we can compare this kilojoules per mole. So we need to find how many moles we produce so we can divide that. Go ahead to do a little stoichiometry, but it's going to be really simple stoichiometry because if you remember what I had earlier, we had that 1 NaOH equals 1 HCl equals 1 water. So everything is just going to be 1 to 1 to 1. So it's going to be really easy stoichiometry here. So starting off with the NaOH, I had 25 grams of it, so that is 25.025 liters of NaOH. It was 1 molar, so that means 1 mole per liter, and it's 1 water per 1 NaOH. Told you that was going to be simple stoichiometry. So we would have made 0.025 moles of water. And the same thing for the HCl. I'm going to consider it just so that we can figure out which one's limiting reagent. You probably can guess because the stoichiometry is, again, so easy. So, since everything is 1 to 1, whichever one we used less of is the limiting reagent. So under our conditions, we would have expected to have made 0.02 moles of H2O. So now we can calculate kilojoules per mole and compare that to the accepted answer. Switch to black. Negative 1.05 kilojoules per 0.0200 moles gives me, I hope you guys are as good in your lab as I am at making up fake data, because I got negative 52.5 kilojoules per mole. Let's do a percent error and we'll wrap it up. Percent error is your observed minus your actual over your actual times 100%. So negative 52.5 minus a negative 55.8, all of that over negative 55.8 times 100 gives me negative 5.9% error. And that is the last step in your calculation. Hopes this helps. If not, get in touch with me and we'll see what we can do.